Welcome to Night Cosmos Sleep, where the deepest stories of space unfold slowly through light, time, and movements almost too subtle to notice. Tonight, we turn toward the constellation Cassiopeiae, not simply to look at a bright star within its familiar W-shaped pattern, but to follow a mystery that has endured for more than half a century. A mystery that did not begin with an object too faint to see, but with a star so bright that it concealed the answer itself. Gamma Cassiopeiae is one such case. On a clear enough night, from many locations across the northern hemisphere, observers can find Cassiopeiae by the 5 stars that form its distinctive W against the sky. Near the middle of that shape lies a blue-white point of light. It does not flicker violently, show any obvious sign of disturbance, or suggest that something around it is generating X-rays far hotter and more powerful than an ordinary massive star should be able to produce. That point of light lies about 550 light-years from Earth. The light we see tonight left the star system centuries ago, before space telescopes, before X-ray detectors, and before anyone knew that the sky contained forms of light entirely beyond the reach of human vision. Invisible light, Gamma Cassiopeiae, appears as a hot, brilliant star among countless others. But if we could see the sky in X-rays, the view would change. At that same location, we would find a powerful, intensely hot, rapidly changing source of energy that does not fit easily within the familiar mechanisms of a massive star. In 1975, as instruments above Earth's atmosphere began detecting X-rays from Gamma Cassiopeiae, astronomers realized they were looking at something unusual. Hot stars can produce X-rays when streams within their stellar winds collide and heat one another. But the signal from this system was tens of times stronger than normal. The plasma responsible for the radiation could reach temperatures of around 100 million degrees or more, while the brightness of the source changed within only a few seconds. A vast region surrounding the star could not easily vary all at once on such a short timescale. That rapid rise and fall pointed instead to a source that was smaller, more concentrated, and far more violent than the star appeared in visible light. For many years, the phenomenon was simply called the X-rays of Gamma Cassiopeiae. The name seemed perfectly reasonable, because the brightest star was also the most obvious object in the system. But light can sometimes draw attention toward the easiest place to look rather than the correct one. Gamma Cassiopeiae is not alone. Beside the massive star is a smaller object, and the two orbit a shared center of mass once every 203 days. The second object is nearly lost in the glare of the primary star. From hundreds of light-years away, separating them is like trying to see a dark stone beside a lighthouse shining directly toward you. That contrast allowed the mystery to survive for more than half a century. One explanation placed the X-rays close to the massive star, where magnetic fields and the surrounding disk of gas might interact, twist, and release energy. Another proposed that the source did not lie on the bright star at all, but near the smaller companion, quietly drawing in some of the gas expelled by its larger partner. Each possibility explained part of the evidence. Neither was strong enough to close the case. Later telescopes revealed more and more detail. They measured the plasma's extreme temperature, detected rapid changes in brightness, and found distinctive iron lines in the X-ray spectrum. These lines were like fine marks within a fingerprint. Some formed in gas so hot that iron atoms had lost nearly all of their electrons. Another appeared when X-rays struck cooler material close to the source. Together, they showed that the environment around the X-ray emitter was far from simple, yet for a long time they still could not reveal with certainty whether the source lay near the massive star or traveled with the hidden companion. The final answer did not come from a new image clearly revealing the mysterious object. It came from an almost imperceptible motion within the iron lines themselves. When a light source moves toward Earth, its spectral lines shift slightly in one direction. When it moves away, they shift in the other. The change is too small for human eyes to detect, and earlier instruments were not sensitive enough to measure it precisely. But with a new generation of X-ray telescope, Astronomers could track the iron lines at different points along the system's orbit, then compare their motion with the movement of each object. If the X-rays came from the massive star, the iron fingerprint should follow that star's orbital rhythm. If the source lay near the companion, the lines should move with the smaller object. The two possibilities produced two different signatures, even though the entire system still appeared as nothing more than a distant point of light in the sky. After more than 50 years, those tiny shifts finally began to reveal what the bright star had been hiding. The X-ray source was not simply located on Gamma Cassiopeiae, as it had once been easy to imagine. Instead, it appeared to be linked to the nearly invisible companion, a small but dense object capable of transforming falling gas into plasma heated to hundreds of millions of degrees. The massive star still dominates the system in visible light, but its high-energy story is unfolding around a much fainter body. In the night sky, Gamma Cassiopeiae still looks like a solitary point of light. Yet behind that simple appearance are two objects orbiting one another: a broad disk of gas, a stream of matter changing direction, and an X-ray source that puzzled generations of astronomers. The smaller object does not need to appear clearly in any image. Its motion has been preserved within the light itself, in iron lines shifting back and forth across a 203-day orbit. Sometimes, the universe does not hide an answer in darkness. It hides the answer in too much light. Gamma Cassiopeiae appears in the sky as a tiny point of light, but the star itself is not small by any measure humans normally use to imagine size. Its mass is estimated to be between 13 and 16 times that of the Sun, with a figure close to 15 solar masses often used to make the scale easier to picture. If the Sun is an enormous sphere of fire, holding the entire solar system within its gravitational field, then Gamma Cassiopeiae is a far hotter, brighter, and heavier star, powerful enough to make the space around it a completely different environment from the relatively quiet regions surrounding our own star. Its light has a blue-white color, a sign that its surface is hotter than the Sun's. From Earth, the human eye cannot clearly perceive that blue tint because a distance of about 550 light-years reduces the entire star to a single point of light. But a spectrum can separate that light into its individual components, much as a prism spreads sunlight into many colors. Within that separation, every element in the star's atmosphere leaves behind a distinctive signature, and those signatures allow astronomers to understand what kind of star Gamma Cassiopeiae truly is. The letter B in the term B star tells us that it belongs to spectral class B, a group of stars that are hot, luminous, and often many times more massive than the Sun. They release much of their energy in ultraviolet wavelengths, beyond the reach of human vision, and may shine thousands or even tens of thousands of times more brightly than the Sun. These are not long-lived stars like red dwarfs, nor do they evolve at the measured pace of the Sun. Their greater mass creates higher pressure and temperature within their cores, causing nuclear reactions to proceed more rapidly, and their fuel to be consumed at a much faster rate. But it is the letter E that makes Gamma Cassiopeiae especially remarkable. In the spectra of many stars, elements usually leave behind dark lines. These lines appear when light from the hotter inner layers passes through cooler gas farther out, where certain wavelengths are absorbed. In B stars, however, some of those lines appear bright instead of dark. The letter E stands for emission, indicating that gas outside the star is producing its own light at specific wavelengths. This gas does not remain still within a smooth, spherical atmosphere surrounding the star. Instead, it gathers into a broad, thin disk rotating around the equatorial region. The disk consists mainly of gas expelled by the star itself. Gamma Cassiopeiae spins so rapidly that its equator moves at an extraordinary speed, making material there more likely to escape than material near the poles. The star is not rotating fast enough to tear itself completely apart, but it is close to the limit at which centrifugal effects begin to play an important role in determining how matter is held to its surface. One way to picture this is to imagine a sphere of water spinning very quickly. As its speed increases, the region around the equator tends to bulge outward, while water near the outer edge is more easily flung away. A star has no solid surface like an ordinary sphere, and the matter inside it is intensely hot plasma, but the image still helps explain why rapid rotation can alter both the shape of the star and the behavior of gas around its equator. Gamma Cassiopeiae is therefore not perfectly round like the sundae. It tends to bulge around its middle, while the regions near the poles are more compressed. Its surface temperature may also be uneven. The poles, where matter is packed more tightly, can be hotter and brighter than the equatorial region. The entire star resembles a sphere of fire flattened by its own rotation, while some of its gas is continually carried outward and added to the larger disk of surrounding material. That disk is not a solid, flat structure, like the rocky rings around a planet. It is more like a thin, transparent layer of hot mist spread widely around the star. The gas remains far less dense than Earth's atmosphere, but because the disk is so large and contains so many hydrogen atoms, it can leave clear and recognizable signatures in the spectrum. When light from the star passes through or interacts with this gas, hydrogen and other elements absorb and re-emit energy in distinctive ways. The emission lines therefore become evidence of a rotating reservoir of material surrounding Gamma Cassiopeiae. The human eye sees only the central point of light, but the spectrum reveals that the star is enclosed within an environment extending far beyond its visible surface. Importantly, this gaseous disk is not the same as an accretion disk falling inward toward the star. In many stellar systems, an accretion disk forms when outside material gradually loses energy and spirals toward a central object. Around Gamma Cassiopeiae, the initial direction of motion is different. Most of the gas is expelled outward by the B star itself and then placed into orbit around it. The disk is the result of the star losing material, not of distant matter pouring down onto its surface. One way to imagine the system is as an intensely hot light bulb spinning within a mist of its own making. Powerful light from the bulb shines through the mist and causes certain regions to glow. The mist does not fall directly back toward the source, but moves around it, spreads outward, and changes over time. During some periods, the disk may become denser. At other times, it may grow thinner, become distorted, or develop an uneven distribution. B stars in general can pass through phases like these. Their gaseous disks do not necessarily maintain the same shape throughout the life of the star. A disk may receive fresh material, expand farther outward, and then slowly disperse. This process is not entirely regular because the release of gas from the stellar surface depends on many factors, from the star's rotation and internal pulsations to changes within its outer layers. Gamma Cassiopeiae is one of the most prominent examples because its disk has been observed for a long time and frequently displays complex variations. Some regions within the disk may be denser than others. The gas does not simply move in perfect circles, but can form ripples, thicker concentrations, or structures that travel slowly through the disk. From Earth, these changes are detected through the way the emission lines in the spectrum grow stronger, become weaker, or change shape. For many years, astronomers focused on this gaseous disk in their search for an explanation of the unusual X-rays. This was entirely reasonable. If intensely hot, rapidly varying plasma and cooler material biases within the same system, the disk surrounding the B star is an obvious place to look first. It already contains gas, it is in motion, and it lies close to a star rotating at extraordinary speed. Interactions between the star and the inner region of the disk could, at least in theory, release energy. But the disk is important not only because it may interact with the star. It is also a reservoir of material that another celestial object may be able to capture. Gamma Cassiopeiae is not a solitary star. Velocity measurements show that it moves in a small, repeating rhythm, as though an unseen object were gently pulling it back and forth. The bright star and its companion orbit a shared center of mass, completing one revolution in about 203 days. Their orbit is nearly circular, rather than stretched into a highly elongated ellipse like those found in many other binary systems. 203 days is not an especially long interval on astronomical timescales. Before Earth can complete a single orbit around the Sun, Gamma Cassiopeiae and its companion have nearly completed 2 orbits around each other. This motion began long before humans first observed the sky through telescopes, and it continues to repeat at a distance of hundreds of light years. From our viewpoint, the 2 objects do not appear as 2 clearly separated points of light. Their true distance from one another may be enormous by human standards, but from Earth, the angle between them is far too small. The B star is also so luminous that it overwhelms almost all the light that might come from its companion. If the second object is a white dwarf, the contrast becomes even more extreme. A white dwarf is only about the size of a planet like Earth, while the B star is larger, hotter, and produces vastly more visible light. The 2 bodies may coexist within the same system, yet in ordinary images, one resembles a brilliant searchlight, while the other is little more than a faint speck, buried beside its glare. The companion does not need to produce much light in order to exert an influence. Its gravity can still pull on nearby material, alter the motion of the gas, and create regions where visible light cannot tell the full story. As the smaller object passes near the outer part of the disk or interacts with material expelled by the B star, some of the gas may be drawn away from its original orbit. This flow of gas does not necessarily form a clearly visible bridge of matter stretching between the 2 stars. The process may be far more subtle. Gas particles orbiting the B star are influenced by the gravity of both objects at once. Some remain within the disk. Some may spread outward and eventually escape the system. Other particles enter a region where the companion's gravity becomes strong enough to redirect their motion. At that point, the disk around the B star is no longer merely a sign of rapid stellar rotation. It becomes the source of material for another process unfolding around a smaller and far more difficult object to see. This creates an intriguing reversal in the way light can mislead intuition. The massive star produces most of the gas in the system. It is also the brightest and most easily observed object, but that does not mean every powerful form of radiation must be generated directly beside it. Matter can leave the star, enter the disk, be pulled into a new orbit, and release most of its energy somewhere else. The B star provides the raw material, while the companion may provide the environment that transforms that material into X-rays. Even so, the existence of the gaseous disk and the 203-day orbit alone was not enough to determine which mechanism was truly at work. The companion had not been seen directly in a way that could clearly establish its nature. The disk around the B star was also complex enough to produce many variations of its own. For a long time, astronomers knew only that the system contained all the ingredients required for several different explanations: a rapidly rotating massive star, a broad disk of gas, an unseen object, and an X-ray source unlike those found around most stars of the same type. Gamma Cassiopeiae itself also demonstrates that classifying a star does not mean all of its mysteries have been solved. Calling it a B star helps describe its temperature, spectrum, rotation, and gaseous disk. But that name does not automatically explain why its X-rays are tens of times stronger than normal, why its plasma reaches such extreme temperatures, or why the signal can change within only a few seconds. A star may belong to a familiar category and still carry a history entirely its own. Gamma Cassiopeiae's present rotation may be connected to an exchange of matter that occurred in the past. The disk surrounding it may be shaped not only by the star itself, but also by the influence of its companion. Features that once seemed separate gradually begin to connect, forming a story of 2 objects that have affected one another over a very long time. If we step back from the terminology, the picture can be held in a simpler form. At the center of the system is a blue-white star with about 15 times the mass of the Sun, spinning so rapidly that it continually sends gas outward from its equatorial region. That gas forms a broad, thin disk moving around the star. Nearby, a smaller object completes one orbit every 203 days. It is far too faint to be seen clearly beside the light of the B star, yet it is by no means separate from the story. The entire system lies about 550 light-years away. From Earth, it still appears as nothing more than a point of light within the W-shaped pattern of Cassiopeiae. But that point contains a star flattened by its own rotation, a constantly changing disk of gas, a nearly circular binary orbit, and a reservoir of material capable of feeding an X-ray source. The gaseous disk may seem to be only the signature of a rapidly rotating star, but somewhere within the system, another object is quietly using that same material as fuel. Visible light from Gamma Cassiopeiae continues to reach Earth just as it has for centuries, carrying the blue-white color of a hot, massive star. But beyond the range of light the human eye can detect, another signal is also leaving that distant system. It carries far more energy, cannot pass through Earth's thick atmosphere, and can be detected only by instruments placed in space. That invisible signal is what turned Gamma Cassiopeiae into one of the most persistent questions in X-ray astronomy. In 1975, when high-energy detectors began observing the star, astronomers realized that it did not behave like most hot stars of similar mass. Gamma Cassiopeiae still displayed many of the familiar features of a B star. It was intensely hot, rotating rapidly, and surrounded by a disk of gas expelled by the star itself. Yet the X-rays detected from the direction of the system were too powerful, too hot, and too rapidly variable to be explained easily by ordinary stellar mechanisms. This does not mean that massive stars produce no X-rays at all. On the contrary, hot, heavy stars often generate powerful stellar winds that continually sweep material away from their surfaces and drive it into space at tremendous speeds. These streams of gas do not always move at the same velocity. One region may travel faster than the material ahead of it, catch up, and collide. When matter is compressed in such collisions, its temperature rises, and some of its energy is released as X-rays. One way to imagine a stellar wind is as several streams of water flowing from the same source without maintaining the same speed. A faster stream from behind eventually catches the slower one ahead, causing the water to bunch together, become turbulent, and convert some of its motion into heat. Around a massive star, the material is not water but plasma, a state of matter in which atoms have been stripped of some of their electrons. Collisions within the stellar wind can heat this plasma to several million degrees, enough to produce X-ray radiation detectable by telescopes in space. For many massive stars, this explanation works quite well. Their X-ray output is usually modest compared with the star's total energy. The plasma temperature also remains within a range that can reasonably be produced by shocks forming inside the stellar wind. The brightness may vary, but it generally does not flare and fade dramatically over intervals lasting only a few seconds. Gamma Cassiopeiae does not follow that pattern. Observations show that the X-ray source associated with the system is about 40 times stronger than what is normally seen from massive stars. The difference is not like one flame burning slightly brighter than the others around it. It is more like discovering an active furnace among embers, expected to release only a gentle heat. The familiar stellar wind mechanism may still be operating around Gamma Cassiopeiae, but it does not appear capable of producing all the radiation being observed. The temperature of the X-ray emitting region is even more unusual. Earlier measurements suggested that the plasma could reach roughly 125 to 150 million Kelvin. In newer analyses, based on iron lines observed by X-rism, the temperature of the ions in certain components has been estimated at around 100 million Kelvin. These values do not necessarily contradict one another. A cloud of plasma does not need to have the same temperature everywhere, and different methods of measurement may be sensitive to different layers of material. One measurement may reflect the hottest portion of the plasma, while another emphasizes a particular group of ions or a specific emitting region. What matters is not choosing a single exact number. Whether the temperature is around 100 million or closer to 150 million Kelvin, it is still far higher than the plasma normally created by collisions within stellar winds. It is even many times hotter than the core of the sundae. At the sun's center, where nuclear fusion continuously transforms hydrogen into helium, the temperature is about 15 million Kelvin. The X-ray emitting region of gamma Cassiopeiae is therefore not merely hot. It belongs to an environment where matter has been accelerated, compressed, or drawn into a strong gravitational field in a far more violent way than ordinary stellar winds can easily produce. Yet extreme temperature is the only unusual feature. The X-ray source also changes in brightness over remarkably short intervals. At times, the signal rises or falls within only a few seconds, as though part of the source had suddenly flared and then quickly subsided. For astronomers, the speed of this variation is more than a minor detail. It places a limit on the size of the region producing the radiation. No change can travel across an object faster than light. If an emitting region were very large, light from its near side and far side would take different amounts of time to reach the observer. Variations occurring across many parts of that region would blend together, making the overall signal change more slowly and smoothly. By contrast, if the brightness shifts clearly within only a few seconds, the source is likely concentrated within a relatively small area. Imagine a vast fire stretching across an open field. Thousands of individual flames are flaring up and dying down at different moments. Even if a few areas change rapidly, the total brightness of the entire field could hardly rise or fall all at once in a single instant. But if the light came from one small flame, concentrated inside a furnace, any fluctuation within it could cause the entire source to change almost immediately. The X-ray source of gamma Cassiopeiae resembles that small furnace far more than a vast burning field. It appears to originate in regions much more compact than the primary star itself. This creates a difficulty for the stellar wind model, because the wind is generated across a broad area around the star, while the rapid variations point toward a small, concentrated location that may lie close to a compact object. Over many years of observation, 3 clues gradually became clear. The plasma was far hotter than what is normally found in stellar winds. The X-ray emission was tens of times stronger than usual, and its brightness could change within only a few seconds. Each feature on its own might not have been enough to eliminate every familiar explanation, but when all 3 appeared together, gamma Cassiopeiae became an exception that was difficult to ignore. Then, within the X-ray spectrum, astronomers found another layer of information. Light, whether visible or in the form of X-rays, reveals more than how brightly an object shines. When separated into different wavelengths or energy levels, it forms a spectrum. Within that spectrum, elements leave behind their own distinctive signatures, as though every kind of matter carries an identifying code. Iron is especially useful in high-energy environments because its atoms contain many electrons and can produce several strong spectral lines when heated or irradiated. In the energy range from about 6.4 to 7 keV around gamma Cassiopeiae, several iron lines appear. The unit keV is simply a way physicists describe the energy of X-ray photons. There is no need to remember these numbers as a formula. What matters is that the lines lie close together, but are not created under the same conditions. Some of the lines appear when iron is present in extremely hot plasma. At temperatures of tens or hundreds of millions of degrees, collisions become so violent that iron atoms are stripped of nearly all their electrons. The remaining iron ions retain only 1 or 2 electrons. When those electrons move between different energy levels, they release X-ray photons with very specific energies. These photons form narrow lines in the spectrum, like the distinct pitch of a bell ringing among many other sounds. These lines show that the source truly contains plasma at an extraordinarily high temperature. They are not merely the result of a model constructed on paper. The iron atoms themselves have left direct evidence of the physical state of the matter where the X-rays are being produced. But another line, near an energy of 6.4 keV, tells a different story. This line does not mainly come from iron heated until nearly all its electrons have been removed. It usually appears when high-energy X-rays strike cooler material in which iron atoms still retain many of their electrons. An X-ray photon from the hot source enters the surrounding matter, collides with an iron atom, and knocks out an electron from deep within it. The atom is then left with an empty space. Another electron from an outer shell drops down to fill the vacancy, and in the process, the atom releases a photon with a characteristic energy. This is iron X-ray fluorescence. The X-ray source can be imagined as an invisible lamp shining onto a wall. The lamp emits one kind of light, but when the wall is illuminated, it responds with a different signature. By observing that response, astronomers know that the lamp is not alone. Relatively cool material must also lie nearby. The simultaneous presence of hot iron lines and the 6.4 keV fluorescent line is therefore extremely important. It shows that the environment around the X-ray source is not uniform. There is a region of intensely hot plasma producing high-energy radiation, but there is also cooler matter close enough to be illuminated by that radiation and emit a signature of its own. This is not the kind of scene usually expected from scattered collisions within a stellar wind. It resembles a more concentrated system in which hot and cool matter coexist within a relatively small space. One region may be producing X-rays, while a nearby surface or stream of gas absorbs and reprocesses part of that energy. From the iron lines, astronomers could begin to imagine an invisible structure. At its center lies the region where the plasma is heated. Around it is denser, cooler material. X-rays from the central region shine onto that matter, causing the iron to fluoresce. Even without seeing its precise shape, the spectrum reveals that the source is not simply an isolated cloud of hot gas drifting freely through space. Each new observation made the picture clearer, but it also made the original question harder to avoid. If the X-rays were truly being produced close to the B star, what on or near that star could create plasma at such an extreme temperature? What could confine the source to a region small enough to vary within seconds? And where was the cooler material responsible for the 6.4 keV iron line? One possibility was that magnetic fields around the B star were trapping and accelerating matter. Although there was no direct evidence for a large-scale magnetic field, smaller magnetic regions might interact with the gaseous disk and trigger bursts of energy release. In that scenario, the hot plasma would lie close to the bright star visible to the human eye. The other possibility shifted attention away from the B star's surface and toward the companion orbiting around it. If that object were sufficiently compact, its gravity could draw in gas from the B star's disk. As the material fell, it would accelerate, collide, and heat up. A small emitting region around the companion could explain the rapid variability more easily than a vast region within the stellar wind. Cooler matter nearby could also produce the fluorescent iron line. For many years, both explanations could use the spectral evidence to support part of their case. The high temperature suggested matter falling onto a compact object, but magnetic activity could also generate hot plasma. The rapid variability pointed toward a small source, but a concentrated magnetic region on or near the B star could also be relatively compact. The fluorescent iron line showed that cool material was present near the X-ray source, but that matter could belong either to the disk around the B star or to a stream of gas surrounding the companion. The mystery therefore persisted not because there was too little data. Gamma Cassiopeiae had been observed many times by several generations of telescopes and across many energy ranges. The problem was that the earlier data mainly revealed the properties of the X-ray source, but could not determine with certainty which object it was moving with. An X-ray spectrum can reveal the temperature, composition, and physical state of matter, but when the resolution is not high enough, the tiny shifts in spectral lines become blurred. The source may be orbiting the system's center of mass, sometimes moving closer to Earth and sometimes farther away. Yet that motion remains hidden within the width of the iron lines. And so, for decades, astronomers knew they were observing an unusual X-ray engine, but they could not place that engine precisely within the map of the system. They knew it was hotter than usual, brighter than usual, and more compact than a simple stellar wind model would suggest. They also knew that cooler matter around it was responding to the radiation, yet all of those clues could still be arranged into more than one possible explanation. Gamma Cassiopeiae was like a room viewed through frosted glass. The light inside revealed the presence of a powerful source of heat. Moving shadows suggested that several objects were there. Reflections on the wall showed that the source lay close to some kind of surface. But as long as the glass remained too cloudy, the observer could not say with certainty which side of the room held the lamp. To determine the true location of the X-ray source, astronomers needed a different kind of measurement. It was not enough to measure how strong the iron lines were, or where they appeared in energy. They had to follow the way those lines shifted over time. If the lines moved with the B star, the source had to lie near the massive star. If they followed the companion instead, the entire story would take a different direction. The iron fingerprints had already revealed an environment containing extremely hot plasma, an unusual amount of energy, and cooler matter nearby. But they had not yet shown whether that invisible engine was hidden within the glare of the B star or traveling with a smaller, darker object along its 203-day orbit. The iron lines in the X-ray spectrum had already revealed that both extremely hot plasma and cooler material responding to the radiation were present around the source. They were like footprints left on the ground after someone had passed by, enough to show that a powerful process was taking place, but not enough to reveal exactly where it had begun. In the Gamma Cassiopeiae system, the X-ray source could lie near the bright star humans had known for centuries, or around a smaller companion hidden within its glare. From Earth, the two locations were almost perfectly superimposed into a single point. That is why the mystery could endure for so long. Astronomers did not lack data, nor did they lack models capable of explaining part of the phenomenon. What they lacked was a signature clear enough to distinguish between two sources lying extremely close together when viewed from more than 500 light-years away. Each generation of telescopes revealed another layer of information, yet for decades, those layers could still be arranged in at least two different ways. The first path kept the X-ray source close to the B star itself. Gamma Cassiopeiae is a hot, massive star rotating at extraordinary speed. That rapid rotation makes gas near its equator easier to expel, forming a broad but thin disk of material around the star. The disk is not entirely quiet. Gas moves through it, regions of different density form and disperse, and material near the stellar surface may continually exchange energy with the surrounding environment. In some models, small magnetic regions on or near the surface of the B star could interact with the inner part of the gaseous disk. Magnetic field lines might be stretched, twisted, and loaded with stored energy. When that structure became unstable, the field could suddenly rearrange itself and release energy into the surrounding plasma. This process is commonly known as magnetic reconnection, but it can be pictured more simply as a rubber band, twisted too far, and then suddenly snapping into a new shape. The stored energy does not disappear. It is transformed into motion, heat, and radiation. On the Sun, similar magnetic processes can produce flares and heat plasma to extremely high temperatures. So when Gamma Cassiopeiae displayed rapidly changing X-rays, some astronomers proposed that comparable events might be occurring close to the star. As long as the magnetic regions were small and concentrated enough, they could explain why the source varied within only a few seconds. If such events occurred continuously in many locations, they could also maintain a strong background of X-ray emission over long periods. This model had a natural appeal. The B star already possessed a broad gaseous disk. It rotated rapidly, and the environment around it was highly active. There was no need to introduce a compact object into the explanation if the interaction between the star and its disk could generate the hot plasma on its own. Some changes in the X-rays also seem to be connected with variations in the disk, making the idea of a source close to the B star appear even more plausible. But the magnetic field remained the most elusive part of the picture. Surveys of many B stars had not detected the kind of large-scale magnetic fields commonly found in certain strongly magnetic stars. That did not mean every form of magnetism was entirely absent. A star might lack a large, stable, easily measured magnetic field while still possessing smaller regions scattered across its surface. Such structures could change rapidly, be hidden by the star's rotation, or produce signals too weak to separate from the star's intense light. For that reason, the failure to detect a large magnetic field was not enough to prove that a magnetic mechanism could not exist. It simply made the hypothesis more difficult to test. If the magnetic regions were too small to measure directly, but were still invoked to explain the X-rays, the model could remain viable without decisive evidence. It had not been ruled out, but neither had it been confirmed in a way that removed all doubt. The second path moved the X-ray source away from the bright star and placed it near the companion. Gamma Cassiopeiae is not alone in space. Its motion reveals the presence of another object orbiting a shared center of mass. About once every 203 days, the two bodies complete one revolution. The companion does not appear clearly in visible light, but its gravity still causes the massive star to move gently back and forth in a steady rhythm. If that object passed through gas expelled by the B star, it could capture some of the material. Gas orbiting Gamma Cassiopeiae did not necessarily remain in the same path forever. Some of it could be pulled away by the companion's gravity, gradually leave the larger disk, and begin falling toward a new gravitational center. As the material descended, it accelerated. Its motion would eventually be slowed in powerful collisions, transforming gravitational energy into heat and X-rays. This idea was not unfamiliar in astronomy. Many X-ray sources in the galaxy are created when matter falls onto a compact object. The crucial question was what kind of object Gamma Cassiopeia's companion might be. One possibility that had been considered was a star stripped of most of its outer layers. In a binary system, one star can expand, transfer matter to its companion, and eventually expose its hot inner core. Such a stellar core could be extremely hot without necessarily being easy to see beside a much brighter B star. If the stripped object continued to interact with surrounding gas, it might contribute to certain forms of high-energy radiation. However, when these models are compared with the full body of evidence, this type of object runs into difficulties. It may account for a few features of the system, but it does not easily produce, all at once, plasma heated to more than 100 million degrees, X-rays tens of times stronger than normal, variations unfolding within seconds, and the distinctive system of iron lines that has been observed. A successful explanation must do more than account for the existence of the X-rays. It must also reproduce the way those X-rays vary, the temperature of the plasma, and the material environment surrounding the source. A neutron star was also once considered a natural candidate. It is the extraordinarily dense core left behind after a massive star ends its life in a supernova explosion. Matter falling onto a neutron star can release enormous amounts of energy because its gravitational field is far stronger than that of a white dwarf. Many B-star systems are known to contain neutron star companions, and they can produce powerful bursts of X-rays when the neutron star passes through or interacts with the gaseous disk surrounding the B star. For that reason, the presence of a B star, an unseen companion, and strong X-rays is not enough by itself to rule out a neutron star. But Gamma Cassiopeiae does not behave like most known B-neutron star systems. Systems containing neutron stars often show distinct outbursts linked to orbital motion or regular X-ray pulses caused by the neutron star's rotation. Gamma Cassiopeiae emits X-rays in a different way, more continuously, less violently than the major outbursts of neutron stars, yet with a high temperature and a very distinctive pattern of variability. The absence of clearly detected rotational pulses also makes the neutron star explanation less convincing. In addition, a system that has survived a supernova explosion may preserve traces of that event in its orbit. An explosion that is not perfectly symmetrical can push the remaining object in one direction, making the orbit more elongated or causing the entire system to move in an unusual way. The orbit of Gamma Cassiopeiae, however, is nearly circular. This does not completely rule out the presence of a neutron star, but it means that such a scenario requires more special conditions in order to fit. The remaining candidate is a white dwarf. A white dwarf is smaller than Earth in size, yet it can contain nearly as much mass as the Sun. It no longer produces energy through nuclear fusion like an ordinary star, but the gravitational field at its surface is still extremely strong. As gas falls toward a white dwarf, the material can accelerate to thousands of kilometers per second. If that flow is suddenly brought to a halt near the surface, the plasma can be heated to tens or even hundreds of millions of degrees. White dwarf systems that are actively accreting matter often leave behind many of the same signatures seen in Gamma Cassiopeiae. They can emit hard X-rays, meaning X-rays with relatively high energies. They show iron lines produced by hot plasma, along with a fluorescent line near 6.4 keV when X-rays strike the surface of the white dwarf or cooler material around it. Their brightness can also change rapidly, because the emitting region may occupy only a small area around the compact object. When each piece of evidence is placed beside the others, the white dwarf gradually becomes an appealing explanation. The high temperature could come from matter falling deep into its gravitational field. The rapid variability is consistent with a small emitting source. The hot iron lines could form in plasma behind the shock, while the fluorescent iron line could appear when X-rays shine down onto the surface of the white dwarf or onto nearby streams of matter. But before measurements became precise enough, this agreement still fell short of decisive proof. Magnetic activity near the B star could also create hot plasma. The gaseous disk around the massive star could provide cooler material capable of producing the fluorescent line. Small regions on the surface of the B star, or just above it, could still vary rapidly. Each clue tilted the story in one direction, but none was strong enough to close the remaining door. The companion itself cannot be seen in any simple way. The B star is massive, extremely hot, and produces an enormous amount of visible light. A white dwarf, even when it is still very hot shortly after forming, is much smaller and has only a limited radiating surface. If it has been cooling for millions of years, its own light would be fainter still. From a distance of about 550 light-years, the two objects also lie so close together that even powerful telescopes cannot easily separate them into two distinct points of light. You might imagine a lighthouse on the coast with a small piece of coal placed directly beside it. From nearby, the human eye could still see both. But from tens of kilometers away, the lighthouse beam would spread through the observing instrument and wash over every dark object beside it. The piece of coal would not have disappeared. It would simply be hidden by the far brighter light. In the case of Gamma Cassiopeiae, the challenge is even greater because astronomers do not merely want to know whether a companion exists. They want to determine what it is. Even if a faint point of light could be separated, it would still need to be analyzed to reveal whether it was a white dwarf, a stripped stellar core, or some other kind of object. Yet the visible light from the B star is so dominant that the spectrum mainly tells the story of the massive star itself and the gaseous disk around it. The irony is that Gamma Cassiopeiae helped astronomers discover something entirely new in starlight long before it became one of the most difficult objects to explain in X-rays. In 1866, the astronomer Angelo Secchi observed the spectrum of Gamma Cassiopeiae and noticed unusual bright lines. In many stars, Spectra usually contain dark lines, formed when gas in the stellar atmosphere absorbs certain wavelengths of light. But in Gamma Cassiopeiae, some of the lines appeared bright instead, revealing the presence of emitting gas around the star. That discovery helped open the way to identifying the class of B stars, B-type stars with distinctive emission lines. From that point on, Gamma Cassiopeiae was no longer merely a bright point in the W-shaped outline of the constellation Cassiopeia. It became a standard object for understanding how hot, rapidly rotating stars create gaseous disks around themselves. For decades, astronomers studied its visible light, tracked changes in its emission lines, and tried to understand how matter was being carried away from the stellar surface. Then, in 1975, the discovery of its unusual X-rays opened a new question. This time, Gamma Cassiopeiae no longer represented B stars in general. It became the prototype of a small group of B stars, with X-ray sources that are powerful, extremely hot, and rapidly variable in a similar way. Over time, astronomers identified around 24 objects with closely related features. They are often called Gamma Cassiopeiae analogs. They are not all exactly alike, but they occupy the same strange middle ground. Their X-rays are far stronger than those of ordinary massive stars, yet they usually do not resemble the major outbursts produced by B-star systems containing neutron stars. Hot plasma, prominent iron lines, and rapid variability appear again and again across the group. The discovery of more similar systems brought both hope and difficulty. If Gamma Cassiopeiae were the only example, it might be explained as the result of some exceptionally rare set of circumstances. But when an entire group of objects shows the same broad signatures, there is a good chance that a shared mechanism lies behind them. Solving the mystery of the prototype star could therefore help explain an entire class of X-ray sources across the galaxy. However, the other systems are no easier to observe. Their B stars are still bright, rapidly rotating, and surrounded by complex gaseous disks. The companion, if it is a white dwarf, remains faint and small. Changes within the disk can obscure or imitate some of the variations coming from the X-ray source. Rather than making the answer immediately clearer, this newly recognized group expanded the debate from a single star to an entire population. In science, two models can coexist for a long time not because one side stubbornly refuses to abandon its idea, but because nature has not yet provided a sufficiently decisive test. Each model must be judged by what it can explain and what it still leaves unresolved. The magnetic interaction hypothesis near the B star has the advantage of linking the X-ray source directly to the visible star and its gaseous disk. The hypothesis of accretion onto a companion, on the other hand, explains the extreme temperature, the compact emitting region, and the iron lines resembling those found in white dwarf systems more naturally. Both have weaknesses. The magnetic model requires fields to exist in a form that has not been directly measured on B stars. The white dwarf model requires a companion to be present even though visible light has not clearly revealed it. The models may reproduce part of the X-ray spectrum, yet still differ in the finer details. When the precision of the data is limited, those differences become blurred, like two paintings viewed through a thin layer of mist. In some years, new observations seem to favor activity near the B star. Changes in the X-rays sometimes appeared alongside variations in the gaseous disk, suggesting that the two regions were connected. At other times, the temperature of the plasma and the iron lines made the white dwarf model seem more convincing. The debate continued to evolve, but it never reached a clear conclusion. What was missing was not another measurement of brightness. Astronomers already knew how powerful the X-ray source was, nor did they simply need another estimate of its temperature, since the presence of extremely hot plasma had been confirmed many times. What mattered more was finding the motion of the X-ray emitting region itself. In a binary system, both objects orbit a common center of mass. When the B star moves toward Earth, its companion moves in the opposite direction along the orbit. Half an orbit later, their roles are reversed. If astronomers could measure the velocity of the X-ray source at different orbital phases, they could determine which object it was moving with. The idea is simple, but carrying it out is extremely difficult. Orbital velocities shift spectral lines by only a tiny amount. Iron lines already have their own natural width because of temperature, turbulent motion, and the resolution limits of the instrument. In older data, the orbital shift could be smaller than, or comparable to, the blurring of the spectral line itself, causing the signal to nearly disappear. What was needed was an instrument capable of distinguishing extremely small changes in the energy of individual X-ray photons. The system had to be observed at several points along its orbit, not just once, and the expected motions of both the B star and its companion had to be known precisely enough to compare them with the measured signal. Once technology reached that level of sensitivity, astronomers no longer had to struggle to see the companion directly beside the glare of gamma Cassiopeiae. They could allow the X-ray source itself to reveal which object it was orbiting with. After nearly half a century, the two remaining explanations were finally placed before a test that they could not both pass. If the iron lines moved with the B star, the source had to lie close to the bright star. If they followed the orbital phase of the companion, then the X-rays were being produced around an object whose visible light still could not be separated from the system. To distinguish between these two paths, astronomers did not need to capture an image of the invisible object. They only needed to listen to the faint motion it had left behind within the X-ray light. For decades, gamma Cassiopeiae was like a room with light spilling through a crack beneath the door, while no one knew where the lamp had been placed. Astronomers had measured its brightness, temperature, patterns of variability, and the traces of iron in its X-rays. They knew the source had to be small, hot, and close to cooler material. But as long as the spectral lines remained too faint and too broad, they could reveal only what kind of properties the X-ray source possessed, not which object it was moving with. What was needed was not a telescope capable of taking a larger picture. From a distance of about 550 light-years, the B star and its companion still lie too close together to be clearly separated in visible light. Astronomers needed an instrument capable of listening to individual X-ray photons with enough precision to detect the slightest changes in their energy. That is the role of X-RISM, an X-ray observatory launched into space to study some of the hottest and most energetic regions in the universe. Its full name describes it as an X-ray imaging and spectroscopy mission. But X-RISM's greatest value does not lie in producing beautiful pictures in the way the human eye usually imagines them. Its strength is its ability to distinguish between energy levels that lie extremely close together, like a pair of ears capable of separating two nearly identical notes within a complex piece of music. At the heart of that capability is an instrument called Resolve. Resolve does not measure X-rays the way an ordinary camera records the colors and brightness of visible light. It works more like an extraordinarily sensitive thermometer. When an X-ray photon enters the detector and is absorbed, the photon's energy does not disappear. Instead, it warms the detector by an extremely small amount. The rise in temperature is so slight that we would never notice it in everyday life, but for Resolve, that tiny change is the key to measuring the photon's energy. A photon carrying more energy warms the detector a little more. A lower energy photon produces a smaller rise in temperature. By measuring each change in heat, the instrument can determine the energy of every incoming photon. Thousands, and eventually millions, of photons are recorded in this way, one particle at a time, gradually building a detailed X-ray spectrum. The sensors inside Resolve are known as microcalorimeters. They must be kept at extremely low temperatures so that the minute changes produced by incoming photons are not lost within the instrument's natural thermal fluctuations. Under these conditions, the detector can recognize temperature changes of only about 1,000th of a Kelvin. That number may sound small, but its significance is enormous. Because of this sensitivity, X-rism can measure the positions of energy lines in an X-ray spectrum far more precisely than many earlier instruments. Resolve can be imagined as the surface of an almost perfectly still lake. If the water is already covered in waves, a falling raindrop will quickly disappear among the larger motions. But when the lake is calm enough, the tiny ripple created by each drop becomes clearly visible. By keeping the detector extremely cold and stable, Resolve turns every photon into a separate ripple of heat that the instrument can measure. When the photons from gamma Cassiopeiae are arranged according to their energy, they do not form a perfectly smooth band of light. At certain energy levels, the number of photons rises noticeably, creating peaks in the spectrum. These lines reveal the elements present in the X-ray emitting region. They resemble the lines of a barcode, with each one connected to a particular physical process and a particular state of matter. Iron leaves behind an especially useful group of signatures. Some lines are produced in plasma so hot that the iron atoms have lost nearly all of their electrons. These lines tell us about the gas that is directly emitting the X-rays. They show that the plasma exists at an extraordinarily high temperature and allow scientists to estimate how the ions are moving within the emitting region. Another line, located near an energy of 6.4 keV, forms in a different way. It appears when powerful X-rays strike cooler material, causing the iron atoms within it to emit fluorescent light. This line does not come directly from the hottest part of the plasma. Instead, it is more like an echo from a nearby surface or stream of gas. It shows that the X-rays have illuminated a denser, cooler region of matter before part of their energy was sent back into space. With X-rism, these lines are no longer merely broad, indistinct bands. Their positions can be measured precisely enough to detect very small shifts over time. And it is here that an effect familiar from everyday life becomes a tool for tracing an invisible object. As an ambulance approaches, its siren sounds higher in pitch. Once it passes and begins moving away, the sound gradually drops. The siren itself has not changed the sound it produces. The difference appears because the source is moving relative to the listener. Sound waves in front of it are compressed, while those behind it are stretched out. Light responds to motion in a similar way. When a light source moves toward Earth, its wavelengths are compressed and the energy of its photons rises slightly. When the source moves away, the wavelengths are stretched and the energy decreases. In visible light, these changes are commonly called blue shift and red shift. In X-rays, scientists track the movement of energy lines in much the same way. The changes in gamma Cassiopeiae are extraordinarily small. The X-ray source is not racing toward Earth at a speed great enough for the human eye to notice any visible difference. But if an iron line that normally sits at a very specific energy shifts slightly upward or downward at different stages of the orbit, that motion can reveal which object the source is traveling with. In a binary system, one object does not simply remain still while the other circles around it. Both bodies move around their shared center of mass. If the B star is more massive, it follows a smaller path. The lighter companion travels along a wider orbit. Even so, at every moment, the two objects remain on opposite sides of the center of mass and move in opposing directions along their orbital paths. When the B star is moving toward Earth, the companion may be moving away. Half an orbit later, the situation is reversed. This means the two hypotheses for the X-ray source make opposite predictions. If the hot plasma lies near the B star, the iron lines should shift with the motion of the massive star. Their energies should rise and fall in step with the B star as it approaches Earth and then recedes. If the X-rays are produced around the companion, the lines should follow the opposite motion. When the B star approaches us, the X-ray source near the smaller object should be moving away, and when the B star recedes, the other source should be moving toward us. The difference is clear in principle, but measuring it requires astronomers to observe the system at carefully chosen times. A single observation reveals only where the iron line lies at that particular moment. To detect orbital motion, They must follow the same line through several different phases, much like capturing a sequence of frames, showing an object traveling around an invisible center. X-rism therefore did not point toward Gamma Cassiopeiae only once and then move on. The observatory studied the system at 3 different times, after the 2 objects had shifted significantly along their roughly 203-day orbit. The first observation took place in December 2024. At that time, the system was viewed at a particular orbital phase when the X-ray source was expected to have a specific velocity along our line of sight. The second observation was made in February 2025, after the 2 objects had traveled through a substantial additional portion of their paths around the center of mass. The third took place in June 2025, allowing the research team to compare the iron lines after the system had entered another state of orbital motion. The 3 observations were not chosen simply to increase the total amount of collected light. They were scheduled at positions where the difference between the 2 models would be easiest to recognize. If the source moved with the B star, the lines would shift in one particular sequence. If they moved with the companion, that sequence would be reversed. You might imagine a Ferris wheel viewed from the side. A cabin on one edge is moving toward the observer, while a cabin on the opposite side is moving away. Even if the cabins themselves could not be seen, and only the sound from one of them could be heard, changes in the pitch would still reveal which side of the wheel that cabin occupied. In Gamma Cassiopeiae, the iron lines play the role of the sound, while the 203-day orbit is the wheel turning silently through space. When the data from the 3 observations were placed side by side, the iron lines did not remain fixed at the same positions. They shifted only slightly, but clearly enough for X-rism to measure. The lines produced by the hot plasma changed over time. The fluorescent line from cooler material shifted in the same general way. This is an important detail. If only the hot lines had moved, the plasma might have been flowing independently within a complex stream of gas. But when both the lines from the hot region and the reflected line from cooler material share the same orbital motion, it suggests that both components occupy the same general area around the source. The lines did not follow the motion of the B star. They changed in the way predicted for the companion. This result is not the same as a direct image of a white dwarf, but physically it is highly persuasive. The light carried the velocity of the place where it was created. When the iron atoms emitted photons, they unintentionally recorded the motion of the entire surrounding region. X-rism only had to read that signature with enough precision to determine which object the emitting region was orbiting with. A bright star may hide a smaller object in visible light, but it cannot erase the Doppler motion of X-rays if the source truly lies somewhere else. The orbit still leaves its mark. Each time the object moves toward Earth, the energy lines shift in one direction. As it moves away, they shift in the other. Across the 3 observations, this pattern emerged as a small but consistent curve. What makes this measurement especially remarkable is that it did not require astronomers to know exactly what the companion looked like in advance. It did not require an image sharp enough to measure its diameter, nor did it require visible light from the smaller object. As long as the X-ray source lay close enough to share its orbital motion, the photons would carry the signature of its velocity. This is one of the ways astronomy repeatedly overcomes the limits of direct sight. Humans cannot travel close to Gamma Cassiopeiae, place a detector beside the B star, or photograph the companions separately with an ordinary camera. But light has crossed that distance for us. Within each photon is information about energy, temperature, chemical composition, and motion. A spectrum, then, is more than a band of color or a collection of narrow lines on a graph. It is a physical record. The hot iron lines describe the plasma. The fluorescent line reveals cooler material being illuminated. The width of each line reflects turbulence or motion within the emitting region. Its shift through different orbital phases reveals the location of the source within the binary system. When all these clues are placed together, the picture begins to change. The X-ray source is no longer a vague phenomenon attached only to the name Gamma Cassiopeiae. It becomes a distinct region of matter with its own motion, linked to the companion orbiting the massive star. The measurement also weakens the explanation that all of the X-rays are produced near the surface of the B star. If the hot plasma were located on or very close to that star, the iron lines would have to carry the B star's velocity, but they do not. They follow the rhythm of the object on the opposite side of the center of mass. This does not mean that all activity near the B star disappears from the story. The star still creates the gaseous disk and still supplies matter to the system as a whole. Interactions within the disk may continue to produce many kinds of variability at other wavelengths. But the hard, hot X-ray source, together with the material producing the fluorescent iron line, appears to be concentrated around the companion. For decades, the two hypotheses survived because each could explain part of the evidence. X-rism did not resolve the debate by making one model theoretically more elegant. Instead, it created a more direct test: which object is the source moving with? The answer was hidden in changes so small that a less sensitive instrument might have missed them entirely. There was no enormous outburst, no new object suddenly appearing in an image, and no single signal bright enough to attract immediate attention. There were only iron lines shifting by a tiny amount between December 2024, February 2025, and June 2025. Yet that slight movement was enough to connect the X-ray source to the companion. When the three spectra were placed side by side, the iron lines did not remain still. They slid back and forth in perfect step with the motion of an object that visible light could not reveal. X-rism's three observations accomplished what generations of earlier telescopes had been unable to do. The iron lines emitted by the hot plasma did not move with the brilliant B star. The fluorescent line produced when X-rays illuminated cooler material did not follow that star either. Both shifted according to the orbital rhythm expected from the invisible companion. This means that the hot gas producing the X-rays and the material reflecting that radiation are most likely located within the same compact region, not immediately beside gamma Cassiopeiae, but around the object moving on the opposite side of the system's center of mass. This result is not a direct image of the companion. X-rism did not see a small sphere emerge beside the B star, nor did it measure the object's diameter or surface, but the motion carried by the light greatly narrowed the remaining possibilities. The source had to be small enough to vary within seconds, compact enough to heat matter beyond 100 million degrees, and surrounded by cooler material capable of producing the fluorescent iron line. Among all the objects that had been considered, an accreting white dwarf became the best-fitting explanation. The name white dwarf may suggest a small, faint star still glowing weakly as it slowly burns, but that is not its true nature. A white dwarf is no longer an ordinary star in the sense that it continues to sustain its light through nuclear reactions in its core. It is the remnant left after a star has passed through most of its life, exhausted the fuel capable of maintaining those internal reactions, and shed its outer layers. The remaining core contracts into an object only about the size of Earth, yet it may still contain a substantial fraction of the Sun's mass. If a white dwarf could be placed beside Earth, the two objects might not appear dramatically different in size, but the white dwarf would have hundreds of thousands of times more mass than our planet. The matter inside it is compressed so intensely that an amount no larger than a small spoonful, if it could somehow be brought to Earth without changing its state, would weigh far more than any human hand could lift. Concentrating so much mass into such a small volume gives a white dwarf a gravitational field near its surface far stronger than that of a much larger but less dense star. A white dwarf does not need to keep burning fuel in order to become a source of X-rays. It only needs matter to fall onto it. In the gamma Cassiopeiae system, that matter is already available. The rapidly rotating B star carries gas away from its equatorial region, forming a broad disk around itself. Most of the gas continues orbiting within the disk, spreads farther outward, or gradually disperses into space. But the companion moves within the same gravitational system, and its pull can redirect some of that material. Instead of continuing around the B star, certain streams of gas are drawn into the region controlled by the smaller object. This process does not necessarily resemble a clearly defined waterfall connecting one star to the other. There is no fixed pipe in space guiding matter along a single route. The gas within the disk has varying densities, moves at different speeds, and is continuously influenced by the gravity of both objects. Some of it may be drawn into thin streams. Some may enter orbit around the white dwarf before falling deeper. Other portions may escape the system or return to the outer regions of the disk. But only a small amount of gas needs to move in the right direction for the X-ray engine to begin operating. As matter starts falling toward the white dwarf, gravity continually accelerates it. Far away, the gas may drift relatively slowly within the B star's disk. But as it approaches the compact object, more gravitational potential energy is converted into kinetic energy. The particles move faster, the flow becomes compressed, and eventually that energy must be released when the motion is brought to a halt. You might imagine a drop of water falling to the ground from a small height. It creates a faint sound and a thin splash. If the same drop falls from much higher above, it strikes the ground faster and releases more energy. Near a white dwarf, the gravitational drop is enormous, and matter can fall at thousands of kilometers per second. When that gas is stopped over a very short distance, its energy of motion does not disappear. It becomes heat, transforming the material into an extremely hot plasma that emits X-rays. This is the heart of the explanation. Gamma Cassiopeiae supplies the gas. The white dwarf provides a deep gravitational well. Matter falling into that well converts gravitational energy into radiation. However, the data reveal more than the fact that material is falling onto a compact object. The shapes of the spectral lines also suggest how the gas approaches the surface. If the white dwarf has no significant magnetic field, the captured material may form an accretion disk, extending almost all the way down to its surface. Within that disk, gas in the inner regions must orbit at very high speeds to balance the pull of gravity. One side of the disk moves toward Earth, while the opposite side moves away. When light from both regions is combined, the spectral lines become broadened by the range of different velocities. You can imagine a circle spinning very rapidly. The left side moves toward the observer, the right side moves away, and points in between have velocities that fall somewhere between those two extremes. If every region emits the same narrow line of light, combining all of those motions will spread the thin line into a broader band. The iron lines of Gamma Cassiopeiae are not as broad as would be expected in such a model. They still reveal motion and turbulence within the plasma, but they do not carry the clear signature of a non-magnetic disk rotating at extreme speed close to the surface of a white dwarf. This makes another structure more plausible. The white dwarf may possess a magnetic field strong enough to prevent the gas from continuing to form a disk in the innermost region. When matter reaches the point where magnetic pressure begins to overpower the gas's orbital motion, it can no longer move freely along the same circular paths. The charged particles in the plasma are forced to travel along magnetic field lines. Instead of spreading around the white dwarf's entire equatorial region, the gas is guided into narrower columns directed toward its magnetic poles. This can be compared to water flowing across a broad surface before being funneled into two narrow pipes. Before encountering the magnetic field, the material may be distributed across a relatively wide area. Once it is guided along the field lines, it becomes concentrated into smaller, denser streams aimed toward a limited number of regions on the surface. The white dwarf is still rotating, but the inflowing matter does not necessarily have to race around close to the surface at the enormous speeds expected in a completely non-magnetic accretion disk. This helps explain why the spectral lines are not excessively broadened. Most of the X-rays may be produced in relatively concentrated regions above the poles, where the gas is falling almost directly along the magnetic field. As the gas approaches the surface, it cannot simply come to a gentle stop. The rapidly moving stream collides with slower material below it. A shock forms above the white dwarf's surface, somewhat like the sudden compression of a supersonic flow when it encounters an obstacle. Here, however, the density, velocity, and gravitational field lie far beyond anything familiar from ordinary life on Earth. Within the shock region, the organized motion of the falling gas is transformed into the chaotic motion of individual particles. Ions collide, electrons gain energy, and the plasma is heated to around 100 million degrees or more. This post-shock material produces most of the high-energy X-rays observed by X-rism. Such temperatures do not require a new nuclear reaction to begin inside the white dwarf. There is no second star reigniting in the ordinary sense. Everything can be produced simply by matter falling and then being brought to a halt. The energy was already stored within the compact object's gravitational field, much like the potential energy held by a rock resting on a mountainside. When the rock falls, that potential energy becomes motion. When gas falls toward a white dwarf, the same principle unfolds on a far larger scale and within a much more extreme environment. The hot plasma behind the shock does not remain at the same temperature forever. It emits X-rays and gradually loses energy. As it cools, the gas continues settling toward the white dwarf's surface. Several temperature layers may exist within the accretion column at the same time. The upper region remains extremely hot. The lower layers have already cooled, and the material immediately above the surface is far denser. This helps explain why the spectrum does not reveal only one temperature, but instead contains several overlapping components. Iron atoms within the hot region leave behind the characteristic lines of highly ionized plasma. But the X-rays produced by the gas column do not all travel directly into space. Some are directed downward toward the white dwarf's surface or strike cooler streams of matter nearby. When high-energy photons encounter iron atoms that still retain many of their electrons, they can knock out an electron from deep within the atom. Another electron from an outer shell then falls into the empty position and releases a new photon. This is the origin of the fluorescent iron line near 6.4 keV. This line is like an invisible reflection. It shows that the X-ray source lies close to a surface or a sufficiently dense region of cooler matter capable of absorbing and re-emitting part of the energy. If the hot plasma is the lamp, the fluorescent line is the patch of light appearing on the nearby wall. Both shift with the orbit of the companion because both the lamp and the wall belong to the environment surrounding the white dwarf. Together, these features create a more unified picture than earlier models could provide. The hot plasma explains the highly ionized iron lines and the hard X-rays. The white dwarf's surface and nearby material explain the fluorescent line. The small size of the accretion region allows the brightness to change within seconds, and the orbital motion of the entire structure matches the Doppler shifts measured by X-rism. The X-ray source, therefore, does not need to be a vast region surrounding the B star. It may be a much smaller structure concentrated around an object roughly the size of Earth, but containing an enormous amount of mass. From a distance of 550 light-years, the entire accretion column cannot be resolved as an image. Yet it still leaves behind a consistent sequence of signatures within the spectrum. Some of the gas begins at the B star, where it is carried away from the equatorial region and joins the broad surrounding disk. The white dwarf's gravity then redirects part of that flow. The material may form an accretion disk or another accretion structure farther out before reaching the region where the magnetic field becomes important. There, the gas is guided toward the poles, falls at tremendous speed, forms a shock, heats up, and emits X-rays. The radiation shines down onto the surface and nearby matter, causing iron to produce fluorescent emission. All of these components move together around the system's center of mass in a cycle lasting about 203 days. This is the X-ray engine inferred from the data. It has no gears, no combustion chamber, and no need for a continuous explosion. Its engine is gravity. Its fuel is the thin stream of gas released into space by the B star. Its guidance system may be the white dwarf's magnetic field, and its luminous region is the shock above the surface, where the energy of free fall is transformed into temperatures of hundreds of millions of degrees. Although this picture explains many of the observed signatures, some room must remain for what the observations have not directly confirmed. X-RISM did not measure the strength of the white dwarf's magnetic field. The shapes of the spectral lines suggest that a magnetic model fits better than a non-magnetic disk, extending all the way to the surface. But that is not the same as a direct measurement of the field itself. Astronomers also do not yet know with certainty how long the white dwarf takes to rotate. In many magnetic accreting systems, the white dwarf's spin can cause the X-rays to vary in a regular rhythm as its polar regions alternately turn toward and away from the observer. In gamma Cassiopeiae, however, the X-ray signal changes in an extremely complex way and has not revealed a clear rotational period that can be confirmed with confidence. The accretion rate has not been fully measured either. The X-ray luminosity allows scientists to estimate some of the matter falling inward, but the result also depends on the white dwarf's mass, the structure of the emitting region, the precise distance to the system, and the fraction of energy released at other wavelengths. It is not yet possible to say exactly how much gas from the B star's disk reaches the companion's surface each second. The geometry of the material flow still allows for several possibilities. The gas may form a small disk before being captured by the magnetic field. It may also travel through unstable streams whose density and direction of infall continually change. The two magnetic poles may receive unequal amounts of matter. One pole may shine more brightly than the other, or the accretion structure may change as the disk around the B star grows denser and then thinner. Even the exact location responsible for most of the fluorescent emission still requires further study. Some of it may come from the white dwarf's surface. Another portion may form within gas that has not yet been fully ionized, or in cooler regions of the accretion structure. Current observations show that the reflecting material lies close to the X-ray source and moves with the companion, but they do not yet provide a complete three-dimensional map. For that reason, the strongest conclusion is not that every detail of the machinery has already been seen. The greater strength lies in the convergence of many different clues. The X-ray source moves with the companion. The plasma reaches temperatures consistent with gas being brought to a halt after falling into the gravitational field of a white dwarf. The hot iron lines and the fluorescent line appear in ways commonly seen in accreting white dwarf systems, and the widths of the lines are more consistent with magnetically guided material than with a non-magnetic disk rotating close to the surface. No single clue provides the entire solution, but when all of them are placed together, a magnetic white dwarf becomes the most natural model for explaining the mysterious X-ray source of gamma Cassiopeiae. In this picture, the smaller star is the place where the greatest amount of energy is released. The B star is far more massive, thousands of times brighter in visible light, and supplies most of the matter in the system. Yet it is the white dwarf, through its small size and concentrated gravity, that transforms a relatively small amount of gas into plasma many times hotter than the sun's core. This is a paradox that appears only when size and power do not go together. A large star may dominate nearly all the visible light from the system, while an object no larger than a planet produces the high-energy signal that has kept telescopes watching for half a century. What matters is not which object is wider, but how deeply the material falls before it is stopped. The gas flow does not need to be dense like an ocean. The disk around the B star is so diffuse that an imaginary spacecraft passing through it might feel almost no resistance in the familiar sense. But the vastness of space allows matter to accumulate continuously, and time allows a small stream of gas to sustain a source of radiation for many years. Each individual particle carries only a tiny amount of energy, yet billions upon billions of particles falling every second can create an X-ray source detectable from hundreds of light years away. This engine does not operate with perfect stability. The B star's disk changes. The amount of matter reaching the white dwarf's region of influence may rise or fall. Gas guided by the magnetic field may break into smaller clumps, causing the X-rays to brighten for a few seconds before fading again. Instabilities within the shock region may continually alter the temperature and density. In this way, the rapid fluctuations in X-ray brightness are no longer an isolated mystery, but a natural result of an uneven accretion flow. Each time a denser clump of gas enters the accretion column, the X-ray output may increase. When the flow becomes thinner, the source grows fainter. Because these changes occur within a compact region, the entire signal can respond quickly. The rapid variability that once caused difficulties for stellar wind models fits much more naturally with a concentrated source near the white dwarf. The fluorescent line may also vary with the amount of cooler material surrounding the X-ray source. When the disk or gas streams provide more matter, a larger fraction of the radiation can be absorbed and re-emitted. When the environment becomes more diffuse, the reflected signature may weaken. Over time, the spectral lines record not only the orbital motion, but also the way the accretion engine changes with its supply of fuel. None of this is visible to the naked eye. Gamma Cassiopeiae remains in the W-shaped constellation, appearing steadily bright throughout a night of observation. No beam of light connects it to the companion. No column of gas rises like a flame. No white dwarf surface is large enough to be photographed by an ordinary telescope. But in X-rays, the system takes on a different form. The B star becomes the supplier of matter. Its gaseous disk becomes a reservoir of fuel. The white dwarf becomes the center of a small, intensely hot accretion region. Its magnetic field may funnel the flow toward the poles. The shock above the surface transforms motion into heat. And iron atoms record the entire process through energy lines that X-RISM can read. The companion, once known almost entirely through its gravitational influence, now leaves behind a wider collection of signatures. It pulls the B star through its 203-day orbit. It carries the X-ray source along with that motion. It heats matter to extraordinary temperatures. And perhaps it also holds within itself a history far older than the radiation now being observed. A white dwarf does not simply appear beside a B star. It must once have been an ordinary star, with a burning core, broad outer layers, and an evolutionary path of its own. In a sufficiently closed binary system, the lives of the two stars cannot remain completely separate. When one star changes size, loses matter, or enters a new stage of its evolution, its companion is affected as well. The X-ray source we see today is therefore not merely the result of gas falling inward at this particular moment. It is the final stage of a chain of events that began long before Gamma Cassiopeiae took on its present form. The star that became the white dwarf may once have been the more massive object, evolving more quickly and transferring some of its material to its companion. The brilliant B star we see today may have received that very matter, gaining mass and spinning faster. Now, part of the flow is moving in the opposite direction. The B star releases matter into its disk, while the white dwarf captures a small portion of it and transforms it into X-rays. The two objects are still exchanging material, but their roles have changed from what they were millions of years ago. The white dwarf therefore does more than explain the X-ray engine now operating around Gamma Cassiopeiae. Its presence also opens a doorway into the past, to a time when the two stars exchanged matter and quietly reshaped each other's lives long before their light ever reached human eyes. The X-ray source around Gamma Cassiopeiae can be understood as the result of matter currently falling onto a white dwarf. But the white dwarf itself is the remnant of a story that began long before the system took on its present form. To understand why a small faint object that has already passed through most of its nuclear life now lies beside a much larger B star, we need to turn back the clock to a time when both were still ordinary stars, born from the same cloud of gas and orbiting a shared center of gravity. At that time, there was no white dwarf, and there was not yet a rapidly rotating B star surrounded by a broad equatorial disk. The system consisted of two young stars with fairly similar, though not identical masses. One was slightly heavier, while the other was lighter. That difference may not have seemed important when the two stars first formed, but over millions of years it determined the entire course of the system's evolution. Inside a star, greater mass produces higher pressure and temperature in the core. Nuclear reactions therefore proceed more rapidly, the star shines more intensely, and its fuel is consumed at a faster rate. A massive star does not live longer, simply because it contains more fuel. It is more like a larger fire, with more material to burn, but an even greater rate of consumption. The lighter star may remain relatively stable, while its heavier companion has already begun to change deep within. The star that was originally more massive in the Gamma Cassiopeiae system therefore evolved first. Hydrogen in its core gradually ran low. Its former internal balance could no longer be maintained, and its outer layers began to expand. The star's radius increased, its surface temperature changed, and the material in its outer atmosphere moved ever closer to the region of space where the gravity of the two stars competed. In an isolated system, an expanding star might retain most of its surrounding gas or lose it gradually through stellar winds. But in a binary system close enough for the stars to interact, the companion changes that process entirely. Each star has a region of space where its gravitational pull dominates. Once the growing star expands beyond that boundary, its outer material no longer belongs securely to it alone. Gas begins to flow toward the other star. This transfer may continue over a long period rather than occurring in a single explosion. The outermost layers are drawn into a stream that passes through the region between the two stars. Some of the gas may spiral around the companion before falling onto it, forming a temporary disk. Some may strike the surface of the receiving star, carrying not only mass but also angular momentum, the quantity that determines how rapidly an object rotates. The star that was once lighter therefore did not remain in its original state. It gained gas from its companion, increased in mass, and was spun up at the same time. You might imagine a slowly turning wheel that is repeatedly struck by streams of material moving in the same direction. Each small amount of gas changes its rotation only slightly, but over a long enough period, the entire star can be driven into a much faster spin. This may be the origin of the B star we see today. Gamma Cassiopeiae is now estimated to contain about 13 to 16 times the mass of the Sun, and it rotates so rapidly that it continually carries gas away from its equatorial region. But that mass and rotation do not necessarily come only from the star's original formation. Some of both may have been given to it by the companion that was once more massive. By receiving matter, Gamma Cassiopeiae did more than grow. In a certain sense, it may also have been rejuvenated, because fresh hydrogen mixed into its inner layers could extend the period during which the star continues to shine so intensely. Meanwhile, the star that donated the material followed the opposite path. As it lost more of its outer layers, deeper regions were exposed. The envelope that had once made it broad and luminous was gradually stripped away, leaving behind a hot but much smaller core. After the remaining stages of evolution were complete and the final layers of gas were removed, that core contracted into a white dwarf. The faint object we see today may therefore once have been the more massive star. This reversal is part of what makes the Gamma Cassiopeiae system so remarkable. Looking at the system now, it would be easy to assume that the brighter, larger, and heavier star must have been the first to evolve. But in many binary systems, history cannot be read directly from present-day appearance. Matter has passed from one star to the other, changing the mass, rotation, and apparent age of both. The star that is now a white dwarf may once have dominated the system. It consumed its fuel more quickly, expanded first, and gave away much of its outer envelope to its companion. The star that began with less mass received that material, becoming heavier, brighter, and faster spinning. After millions of years, their roles were almost reversed. The former donor became the smaller object, while the former recipient became the dominant source of light. This reversal is sometimes described as the mass paradox in binary star systems. It is not a paradox in the sense that any law of physics has been broken. It simply shows that a star's mass does not always remain constant throughout its life. In a close binary system, the two stars do not evolve as isolated objects. They share matter, angular momentum, and the consequences of every major change that unfolds along the way. If we could observe the system far back in the past, we might see an almost opposite picture. The star that has now become a white dwarf may once have been brighter, larger, and faster at consuming its fuel. Gamma Cassiopeiae may then have been smaller, rotating more slowly, and not yet surrounded by a broad equatorial disk. The original flow of matter moved from the star that evolved first toward its companion, gradually building the B star we see today. Now, a very small portion of that flow appears to have reversed direction. Gamma Cassiopeiae rotates rapidly and releases matter from its equatorial region, creating the gaseous disk around it. The white dwarf moves through this environment and captures some of the gas. Matter that once traveled from the first star to the second in the distant past is now leaving the B star and falling back toward the dead stellar core. The present-day flow is far smaller than the major episode of mass transfer that occurred long ago, but it is still enough to create plasma hundreds of millions of degrees hot and an X-ray source detectable from a distance of 550 light-years. The system therefore carries a kind of physical memory. Gamma Cassiopeiae's rapid rotation preserves traces of the matter and angular momentum it once received. The white dwarf is the remaining core of the star that evolved first. The present gaseous disk may be a consequence of the fast rotation produced by that ancient exchange. And today's X-rays appear when some of the material returns to the object that once gave it away. No part of this record is written in words, yet the history remains preserved in the system's masses, orbit, rotation rates, and radiation. Astronomers read that history by combining many kinds of data. Orbital motion shows that the two objects are gravitationally bound. Visible light spectra reveal the nature of the B star and its gaseous disk. X-ray iron lines identify the motion of the hot plasma. Models of binary evolution connect the system's present state to a past capable of producing it. Even so, the specific history of Gamma Cassiopeiae cannot be replayed like a film. No one directly observed the major mass transfer episode that took place millions of years ago. What scientists reconstruct is a scenario consistent with the laws of physics and with the system's present form. It is strongly inferred from the presence of a rapidly rotating B star beside a compact object, from the likelihood that this object is a white dwarf, and from the broader understanding of how binary systems evolve. If the companion truly is a white dwarf, then an earlier period of mass transfer becomes a natural part of the story. A star must lose its outer envelope before its core can become a white dwarf, and in a close binary system, the companion is the most likely place for some of that material to go. The same process also provides an efficient way to spin up the B star. The two parts of the story help explain one another. This gives Gamma Cassiopeiae significance far beyond a single X-ray source. Models of binary evolution have long predicted that many B stars were not born with all of their rapid rotation. A substantial number may have been spun up by receiving matter from an evolving companion. After losing its outer layers, that companion could become a white dwarf. The galaxy may therefore contain many systems made of a bright B star and a faint white dwarf, even though most of them are difficult to recognize. Some population models have estimated that roughly 50 to 70% of binary systems containing B stars could include white dwarf companions. This does not mean that more than half of all B stars in the sky are certainly accompanied by white dwarfs. The estimate depends on how the population is defined, the star's initial masses, the distance between them, and the efficiency of mass transfer. Even so, the prediction suggests that B white dwarf systems may be far more common than the number of confirmed examples would imply. The reason for the gap between prediction and observation lies in the light itself. A large, hot B star can produce an enormous amount of visible light. The white dwarf beside it is only about the size of Earth. Unless it is accreting matter strongly, it contributes very little to the combined spectrum of the system. Even while the white dwarf is still hot, its light can easily be overwhelmed by the B star. The two objects also appear too close together in the sky for ordinary telescopes to separate them into two distinct points. Many such systems may have been observed for years without anyone realizing that a smaller object was present. The spectrum is dominated by the B star. Images show only a single point of light. Orbital motion may be too subtle to detect, or it may require years of monitoring. If the white dwarf does not capture enough matter to produce significant X-rays, there may be almost no clear signal forcing observers to notice it. Gamma Cassiopeiae is different because it contains a powerful and unusual X-ray source. Matter from the B star's disk provides enough fuel for the companion to leave behind a high-energy signature. The X-rays prevent the system from completely hiding its structure. The iron lines have carried the companion's motion out from beneath the glare of the B star and into a form that can be measured. If the new interpretation is correct, Gamma Cassiopeiae may be the first clearly confirmed example of a class of systems predicted for decades. It would no longer be only an unusual B star, but a vivid example of a post-mass transfer system, in which the star that received matter became a B star, while the donor contracted into a white dwarf. The objects resembling Gamma Cassiopeiae make this possibility even more important. In some samples of nearby early-type B stars that can be studied in sufficient detail, about 10% show X-rays with Gamma Cassiopeiae-like properties, stronger than normal, extremely hot, marked by distinctive iron lines, and rapidly variable. That fraction is large enough that the phenomenon cannot be dismissed as a single coincidence, but it still does not allow astronomers to conclude that every Gamma Cassiopeiae-like star definitely contains a white dwarf. Stars can produce similar phenomena through more than one path. Some systems may contain magnetic white dwarfs. Others may have different accretion structures. It also remains impossible to rule out completely that a few objects generate their X-rays through activity close to the B star itself. Gamma Cassiopeiae is the most thoroughly observed example, but every other system will still require its own orbital and spectroscopic evidence. The iron lines must be tracked across several orbital phases. The motion of the X-ray source must be compared with the motions of both the B star and its companion. Only when the same kind of signature appears repeatedly in multiple systems will astronomers be able to determine whether Gamma Cassiopeiae is the prototype of a common mechanism or simply the most prominent member of a more diverse group. Even if a white dwarf explains the X-ray source well, another question emerges from the masses of the B stars in this class. Population evolution models often predict many B white dwarf systems around B stars of lower or intermediate mass. The reason lies in the way stellar lifetimes, mass transfer, and orbital stability interact. Yet Gamma Cassiopeiae-like objects are often found around B stars that are relatively massive and hot. There may be several reasons for this difference. Systems around lower mass B stars may exist, but be too faint in X-rays to detect easily. More massive B stars may produce denser gaseous disks or supply matter more efficiently, causing their white dwarf companions to shine more brightly in X-rays and making them easier to find in surveys. In that case, current observations may be revealing only the brightest part of a much larger population. It is also possible that existing models do not describe the transfer of matter between the two stars with complete accuracy. Some gas may escape the system instead of falling onto the companion. Angular momentum carried away by that outflow may alter the orbit in complex ways. The star receiving the material may reach its rotational limit before it can accept all the gas predicted by simpler models. Each of these details affects the final mass of the B star and the number of B white dwarf systems that remain. There may also be evolutionary stages that have not yet been fully accounted for. Magnetic fields, stellar winds, internal mixing, and oscillations within the stars can all change the pace of their evolution. A small error at each stage, when applied across millions of simulated systems, can create a large difference in the final population. Gamma Cassiopeiae therefore answers one question while placing new pressure on broader models. If the X-ray source truly comes from an accreting white dwarf, those models must explain why the system contains such a massive B star today, why the orbit is nearly circular, and why the accretion process produces this particular kind of X-ray emission. The answer may require adjustments to the way mass transfer, angular momentum, and gas loss from the system are calculated. At present, some parts of the picture have been measured with considerable confidence. The Gamma Cassiopeiae system has an orbital period of about 203 days. Its X-ray iron lines change with orbital phase. Their motion is consistent with the companion and inconsistent with the X-ray source being located on or very close to the B star. These are direct signatures in the data. From those measurements, a strong layer of interpretation can be built. The companion is most likely a white dwarf. The X-rays are produced when matter from the B star's disk is captured, falls inward, and releases gravitational energy. The relatively narrow shapes of the spectral lines fit better with a magnetic white dwarf, where gas is guided toward the poles, than with a non-magnetic accretion disk rotating close to the surface. But many features have not yet been measured directly. The strength of the white dwarf's magnetic field remains unknown. No secure spin period has been identified. The exact amount of matter falling inward each second is uncertain. The three-dimensional structure of the flow, the locations of the magnetic poles, and the contribution of the white dwarf's surface to the fluorescent line have not yet been fully mapped. The history of mass transfer also contains important gaps. The initial masses of the two stars are not known precisely. It remains unclear how much matter was transferred to Gamma Cassiopeiae and how much escaped from the system. The B star's original rotation rate and the time when mass transfer ended cannot be determined with certainty. Models can reconstruct a plausible past, but several different histories may still lead to a system resembling the one we see today. Whether all Gamma Cassiopeiae-like stars share the same mechanism remains an open question. Some may be white dwarf systems. Others may contain different companions or display unusual magnetic activity. To distinguish between them, astronomers must repeat the measurements of X-ray line motion in each system, a task that requires long observing campaigns and instruments with high spectral resolution. This incomplete picture does not reduce the value of the discovery. On the contrary, it shows how science often advances by gradually narrowing the range of possibilities. Previously, the X-ray source could have been located near either the B star or the companion. X-RISM's data have shifted the answer strongly toward the companion. Among the objects that could exist there, a white dwarf explains the greatest number of features. From that point, a history of mass transfer becomes a logical way to produce both the white dwarf and the rapidly rotating B star. Each step rests on the one before it, without requiring every interpretation to be treated as absolute certainty. What has been measured remains separate from what models are used to explain. What is still unknown remains open to future observations that may reshape the picture. At a distance of 550 light-years, the two objects continue to move as they have for a very long time. Gamma Cassiopeiae, the star that may once have been lighter, is now the brightest object in the system. The white dwarf, the surviving core of the star that evolved first, has nearly vanished beneath the visible glare. Between them, a small stream of matter is repeating, in the opposite direction, the exchange that once transformed them both. Gas leaves the B star, enters the disk, is drawn toward the white dwarf, and falls into regions near its poles. Gravitational energy becomes heat. The plasma emits X-rays. Iron atoms record the motion. The photons leave the system and cross the darkness between the stars for more than 5 centuries before finally reaching X-RISM. Within each of those photons lies more than information about a hot shock unfolding in the present. It also carries traces of a much longer history, when one star expanded, gave its outer layers to its companion, and then contracted into a small surviving core. The star that received the material became a B star. The star that gave it away became a white dwarf. And after millions of years, some of that matter began to return. A mystery lasting half a century has found its most convincing answer to the question of where the X-rays are coming from. But the story does not end there. It simply expands from a single star system into an entire population that may be hidden throughout the galaxy. If Gamma Cassiopeiae truly is a B white dwarf system, how many other bright stars are concealing small companions of their own? How many white dwarfs are quietly capturing gas from vast disks of matter, producing X-rays too faint or too distant for current surveys to detect? And how many B stars carry their rapid rotation as a lingering memory of mass transfer that took place millions of years ago? One question has been narrowed, but behind it lies an entire region still waiting to be explored. The mystery is no longer only about where the X-rays come from. It has become a question of how many similar systems remain hidden within the light of the Milky Way. Below is the complete conclusion, gradually easing the flow of information, returning to the night sky, and closing with a reflection on how science discovers what cannot be seen directly. As the story returns to the night sky, the constellation Cassiopeiae is still there, a quiet W among the northern stars. Gamma Cassiopeiae remains nothing more than a tiny blue-white point of light, far too small for the human eye to recognize any of the structures surrounding it. We cannot see the thin gaseous disk spreading around the B star's equator. We cannot separate the white dwarf from the glow of its larger companion. We cannot see the stream of matter leaving its former path, being drawn toward a small center of gravity, and accelerating through the darkness between the two objects. Nor can we see the shock above the white dwarf's surface, where the falling gas is brought to a halt and heated to hundreds of millions of degrees. Everything is too distant, too small, and beyond the range of light our eyes can detect. Viewed from the ground alone, that entire complex system still collapses into a single, almost motionless point. But that stillness belongs only to the distance. Within the Gamma Cassiopeiae system, the two objects continue orbiting a shared center of mass every 203 days or so. The B star is still rotating at tremendous speed and releasing gas into space, replenishing the thin disk around it. The white dwarf continues moving through that material, capturing a tiny fraction and drawing it into its gravitational field. Streams of matter fall inward, heat up, and emit X-rays. Before that radiation begins its roughly 550-year journey toward Earth. Each photon leaving the system carries only a minute amount of energy. Yet it also carries information about the place where it was created. Its energy reveals the temperature of the plasma. The characteristic lines of iron reveal which material is present. The widths of those lines preserve traces of motion within the emitting region, and their tiny shifts from one orbital phase to another show whether the entire X-ray source is moving toward us or away. Through changes that are almost impossible to notice, an object that appears clearly in no ordinary image has left its motion encoded within the light. This is also one of the ways astronomy continually extends the boundaries of sight. We do not always need to photograph an object in order to know that it exists. A distant planet can be discovered when its gravity causes its host star to shift ever so slightly. A black hole can be recognized through the motion of hot gas around a dark region or through the orbits of nearby stars. Dark matter emits no light, yet its gravitational influence appears in the movement of galaxies and in the way light bends as it travels through space. The white dwarf in Gamma Cassiopeiae was found in much the same way. It did not step out from the B star's glare and appear as a clearly defined sphere. It revealed changed energy as the X-ray emitting region moved along its orbit. A tiny shift in the spectrum accomplished what visible light could not. It showed where the high-energy engine was truly operating. The story reminds us that light does more than allow us to see the universe. Light also preserves the universe's memory. A single photon may carry traces of temperature, velocity, chemical composition, and the gravitational field of the place where it was born. When enough photons reach an instrument sensitive enough to read them, those individual traces begin to assemble into the history of an entire star system. And the history of Gamma Cassiopeiae reaches far beyond the 50 years during which humans debated the origin of its X-rays. Millions of years ago, the two stars in the system did not evolve separately. The star that began with more mass consumed its fuel more rapidly, expanded, and transferred part of its outer envelope to its companion. The receiving star gained mass, acquired additional angular momentum, and began rotating faster and faster, gradually becoming the brilliant B star we see today. The star that had once been larger lost its outer layers and contracted into a small white dwarf. In the past, matter flowed from the star that is now the white dwarf toward the star that is now Gamma Cassiopeiae. Today, a very small portion of that material is traveling in the opposite direction. Gas leaves the B star, joins the disk, is captured by the white dwarf, and falls toward regions near its poles. A process that once transformed the lives of both stars appears to be continuing, but now in a smaller and quieter form. The X-rays from Gamma Cassiopeiae are therefore more than a sign of extremely hot plasma. They are the luminous expression of a gravitational relationship that has endured through several stages of stellar evolution. They carry traces of an ancient exchange of matter, of the star that once gave away its envelope, of the star that received that material and began to spin faster, and of the reversal that left the formerly larger object as the smallest member of the system. By the time those X-ray photons reach Earth, they have crossed interstellar space for longer than the entire history of many civilizations. They began their journey before people on Earth knew of telescopes, before we understood that light could be separated into a spectrum, and before we knew that the sky was filled with invisible forms of radiation. Then they struck a detector held at an extremely low temperature. One photon warmed the sensor by an almost immeasurable amount. Another arrived after it, followed by thousands and then millions more. From changes in temperature so small they would otherwise seem insignificant, scientists reconstructed the motion of an object hundreds of light years away. There is something deeply quiet about the way the answer emerged. There was no moment when the white dwarf suddenly became clearly visible in the sky. No explosion revealed the entire system at once. There were only iron lines shifting ever so slightly between three observations, enough to show that the X-ray source was not following the massive star, but moving with its companion. After more than half a century, the mystery was not solved by staring more powerfully at the point of light, but by measuring more precisely what the light was carrying. Perhaps that is also the deeper meaning of this story. What stands out most is not always where the most important events are taking place. The B star dominates nearly all the visible light, yet the faint white dwarf is where the extremely hot plasma is being created. The largest object does not necessarily determine the course of the story. Sometimes, a body no larger than a planet can control the flow of energy that keeps an entire system mysterious for generations. In life, as in science, the most visible things often attract most of our attention, but the deepest cause may lie in a slight motion, a faint signal, or a component almost completely hidden from view. Finding it does not always require a dramatic moment of discovery. Sometimes, all that is needed is enough patience to observe the same system over many years, enough care not to overlook a tiny shift, and enough humility to preserve several possibilities until the data can distinguish between them. Gamma Cassiopeiae had been known to humanity long before its X-rays were discovered. Its emission lines helped open the way to the concept of B stars. Later, it became the prototype of a group of stars with unusual X-ray emission. Now, that same system may be providing evidence for a class of B white dwarf binaries predicted long ago, yet still largely hidden throughout the Milky Way. An answer, then, does not make every question disappear. It simply changes the shape of what remains unknown. The question was once where the X-rays were coming from. Now it has become how many other B stars are hiding white dwarf companions. How many small objects are quietly capturing gas and producing X-rays too faint to be recognized. How many rapidly rotating stars carry within their motion the memory of mass transfer that occurred millions of years ago. Some similar systems may lie within points of light that humans have observed many times without ever fully understanding them. They do not need to be completely dark in order to remain unnoticed. They only need to stand too close to a brighter star. Tonight, if the W-shaped outline of Cassiopeiae appears in the sky, Gamma Cassiopeiae will look no different than before. It will still be only one point of light among many others. There is no way to know with the naked eye that a gaseous disk, a white dwarf, and a region of plasma many times hotter than the sun's core exist around it. But no longer being able to see something does not mean we cannot know it is there. We know that two objects are orbiting one another. We know that a stream of gas is passing between them. We know that iron atoms have recorded the velocity of the emitting source. And we know that an almost invisible object has left a signature clear enough to cross more than 500 light-years and be recognized here on Earth. Perhaps that is the most beautiful thing the story of Gamma Cassiopeiae leaves behind. The vast universe does not always speak through explosions or brilliant objects. Sometimes, it leaves only a tiny change in the energy of light, then waits for a civilization patient enough to learn how to read it. As we slowly drift away from the W of Cassiopeiae and return to the stillness of the night, those two stars continue along their orbit. The B star continues to shine. The white dwarf remains almost invisible beside it. Small streams of gas continue to fall, heat up, and emit X-rays. And new photons begin their long journey toward Earth, carrying a story that will not be read for centuries. May we remember, whenever we look toward a distant point of light, that what the eye can see is only the first layer of the universe. Behind one star may be an invisible companion. Behind one bright line may be the motion of an entire system. And behind the quiet appearance of the sky may lie stories that have been unfolding for millions of years. Sometimes, the smallest and faintest object in a system is where its brightest story is taking place.